SwayamPrabha. Digital India. Educated India.
Hello all. In this video we'll be looking at the micromechanics of the lamina, where we look at both stiffness and the strength. This will be a continuation from the previous video where we already discussed about stiffness prediction in using micromechanics. So there is one small topic which is left over, which will take it up in this video, and then move on to the strength prediction also using the micromechanics. So with this video we will be completing the micromechanics topic, and from the next video we get to the main topic of this week's topic, which is the mechanics of laminate. So let me start with the outline. So in the previous video we have covered this, where we use the mechanics of materials approach to predict the stiffness of the lamina. In today's video we will see a semi-empirical approach which is quite simple to apply in the designs, where we want to predict the stiffness of the lamina. Again, stiffness prediction meaning we are talking about, can we find the values of E1, E2, Poisson ratio and the shear modulus when we know the properties of the fiber and the matrix material. And after this we will also talk about the strength prediction, where we'll be talking about two different approaches. The first, we assume that all fibers have equal strength, and second, we take into consideration that all fibers failing instantaneously, it's not a reality, but then if there is a distribution, how to approach about it. Okay. So here is the recap of the previous video, where we discussed about how we use the mechanics of the materials approach. We mentioned previously saying mechanics of materials approach is where we make approximations or assumptions. These are simplified assumptions which lets us to derive these simple relations for all the stiffness parameters. So we started with E1. We got a rule of mixtures formula which we said is fiber dominated. For E2, we got a inverse rule of mixture which we showed it as to be matrix dominated. And for Poisson ratio, we said that it is a rule of mixture formula which is neither fabric dominated, which is neither fiber dominated nor the matrix dominated. And for the shear modulus, we again showed that it is a inverse rule of mixture which is matrix dominant. So this is what we have seen with the mechanics of materials approach, but there are other approaches also to do these stiffness predictions. So mainly the elasticity approach, where we rigorously apply the equilibrium equations, compatibility equations and the stress strain relations to find what is the stiffness E1, E2 and the Poisson ratio and the shear modulus. Though because of the limitations of the time, we are not going into those specific models, but in summary what we notice from this approach is usually these equations or curves are very complicated. These are not simple equations which can readily be used when designing. And the second disadvantage is they are restricted to small design regions. What it means is those equations or the curves which we derive using this approach are usually limited to a certain volume fractions or a certain kind of fibers. Either it could be shape of the fiber or the distribution of the fibers. So though it is a very exact approach and which is more accurate, but then because of these complexities involved, it is not very useful in the design. So there is an other midway where we use the Halpin-Tsai equation. This is a semi-empirical approach, meaning these are not directly empirical, meaning they are from experience. These are not just curve fitting, but these we use the knowledge we have gained from the elasticity approach and then simplify those equations by doing a bit of curve fitting. So we use both the analytical approach as well as the curve fitting to come up with these Halpin-Tsai equations. So as I'm mentioning, the reason why these Halpin-Tsai equations are very commonly used in industry is because they are simple and ready to use in the design. And these are actually a generalization of the micromechanics equations. So these equations are inspired from the elasticity approach where we derive and show the exact equations. Before we start discussing about Halpin-Tsai equation, there is one more comment I want to make regarding these E1 and Poisson ratio nu12. As you can see, we have derived these using the mechanics of materials approach, and in both cases we have the simple rule of mixtures. So in fact, for both of these, the comparison with the experiments is quite good, which means the simple equations we got here using the mechanics of materials approach are good enough even they compare with the elasticity approach as well as with the experiments. Whereas E2 and the shear modulus G12, these are the two stiffness parameters which doesn't match exactly with the experiments. That's where we try to modify only these two expressions, only E2 and G12. We focus on these expressions and see how we can simplify these analysis. So coming to the Halpin-Tsai equations, as you can see, the E1 and nu12 are again just repeated from the mechanics of materials approach. So both of them are simple rule of mixtures. But when we discuss about G12, the shear modulus, and the transverse elastic modulus E2, this we replace with M to make things common. So whenever I write here M, it could either mean the shear modulus G12 or the transverse elastic modulus E2. So the relation is the same for both these shear modulus and transverse elastic modulus. And if you look at this equation, it is written in terms of three quantities. We have the Z, eta, and the volume fraction of the fibers Vf. So Z is the measure of the fiber reinforcement. So it depends on various parameters which include the fiber geometry, whether the fibers are circular cross section or square or rectangle cross section. Depending on this cross section, this Z value changes. It also depends on the packaging geometry, meaning when there are multiple fibers, whether they are equally spaced both in X and Y versus differently spaced in X and Y. And you could also say whether they are randomly spaced or there is a pattern which it is following. So depending on the packing geometry, also the value of Z changes. And lastly, it depends whether what kind of loading, meaning this Z value may not be the same for both shear modulus and transverse elastic modulus. So let's say that we are talking about a circular cross section, and let's say even the packing geometry is even, meaning the distances in the X and Y directions are the same. But then whether we are applying a shear load versus whether we are applying a lateral load, this Z can have a different value. Okay. So Z is actually uh, the curve fitting parameter which connects with the experiments. So how do we get this Z value? We do some experiments and then fit this equation to those experimental data to get the Z value. So once you get the Z value, then I'll show you later we can also get the eta value. But now let's see what is the intuition we can get from these Z values. So what is the range of Z values? What is the minimum value it can take and what is the maximum value it can take? If you look closely, you will see that these values range from 0 to infinity. 0, when you take it as 0, what we get is the inverse rule of mixtures. So I think we are familiar with this inverse rule of mixtures. In fact, this is the formula we got from the mechanics of materials approach. For the inverse rule of mixtures, we said it is a lower bound. So let me explain what we meant by lower bound and upper bound. So let's say the x-axis is the volume fraction of the fibers. Previously we mentioned uh, the left side is the complete matrix and the right is the complete fibers. So since we know that the properties of the matrix are low, we start with a small value and reach the higher properties of the fiber material. And the y-axis could be any of the stiffness parameters we are looking at. It could be E1, E2, the shear modulus, or the Poisson ratio. Not exactly for the Poisson ratio, but for the other, because we said Poisson ratio, they are comparable. Okay. So if it is a rule of mixtures, the way we draw the curve is it's a straight line connecting these two points. And for the inverse rule of mixtures, we said it is a curve with so and so fashion. Okay. So now what we are saying is this inverse rule of mixtures, we are calling it as the lower bound. And the upper bound is in fact the rule of mixtures. Okay. So here what we are saying about z value is when z is equal to 0, we get to the inverse rule of mixture, which is the lower bound. Let me write it as z equal to 0. And the upper bound or the rule of mixture is when we take z as infinity. Okay. So these are the two extremes, but in reality the values are in between these 0 and infinity. So it could be some curve somewhere in between. So since there are infinite curves between the lower bound and the upper bound, the exact curve will depend on the value of z. Okay. So now let's come and discuss about also this the second parameter, which is eta. Eta is given in terms of the fiber and the matrix properties as well as z. So since we said we know the properties of the constants, we know these mf and values, and this z we are getting from the curve fitting. So let's say we also know z. So if we know this, then one should be able to find or calculate eta value. And then even eta has some physical significance. These values range from rigid inclusions the value is 1, for homogeneous materials the value is 0, and for voids it can be written in terms of 1 by z, minus 1 by z. With this we conclude this topic of the Halpin-Tsai equations, where we have shown these simple equations to predict the stiffness properties of the lamina. So now that we have looked into few of the topics on the stiffness prediction, we'll now start discussing about the strength prediction. Before we start discussing about these strength prediction models, we should be clear about one thing, saying that our understanding of the stiffness is much greater than our understanding of the failure. So this is the same not just for composites, but also for regular metals or any other materials. So these models what we'll be discussing are very preliminary, and actually much work needs to be done before we can come up with models which are totally based on fundamental concepts. So with this brief introduction, let's see what is our understanding about the strength prediction. So first let's comment on the fibers and the matrix. So usually fibers are much stiffer and stronger compared to the matrix materials, and usually these are less ductile than the matrix materials. Most often the fibers are brittle, like for example glass fibers. These are very brittle compared to the matrix material, let's say is epoxy, which is more ductile compared to the fibers. And usually have already discussed and said that fibers are much stiffer and stronger. That's the reason why we do reinforce these matrix materials with the fibers. Now let's see how the stress strain response is for a fiber and for a matrix. So let's start with the matrix material. So at small strains, it is usually linear, but after that, it goes into the plastic region. But for fibers, usually these are stiffer, so the slope will be high. Let's change the color. But after a particular amount of stress and strain, they also change to plastic behavior. So there is a region where they are linear elastic and then they go into the plastic behavior. So let's also show that where these fibers fail and where the matrix fails. So though it is not to scale, basically what we are trying to show is the fibers fail first and then the matrix, because matrix is usually more ductile, it can take much more strains. Okay. So once we have seen that both the fiber and the matrix have linear elastic behavior at the beginning and then come to the plastic behavior, these are not true for all materials, because you can always come up with few fibers where there is only linear elastic behavior and there is no plastic behavior. But what we are trying to show here is more general, which can be applied for both any kind of fiber or any type of matrix material. Okay. So if this is the case, usually the composite behavior will be in between the matrix curve and the fiber curve. So for the composite, since both fiber and matrix are initially linear, the composite also will be linear until the matrix starts going into plastic. That's when even the composite transfers, moves into the plastic region. Okay. So let me note it down that this is for composite. So looking at this plot, we should be able to see that there are different regions. So let's say if you are looking from zero strain to the strain at which the matrix transforms from linear to plastic, this let's say is stage 1. So here we look into, as we are loading for a unidimension, as we are loading for a unidirectional composite, we get to the stage 1 at small strains. So in this stage 1, we see both the fiber and the matrix both deform elastically. But if we continue loading, what happens? So now the matrix goes from elastic to plastic region, whereas the fiber continues in the elastic region. So let's say this is the stage 2, this is 1. So in stage 2, we have fiber deforms elastically, whereas the matrix deforms plastically. But if we keep loading, then we move into stage 3 until the fiber fails, because fiber is the one which fails first if we are considering strain as the failure criteria. And if we continue to load, then if the matrix is able to sustain the load, then we go into this stage 4. So stage 3 is both fiber and the matrix deform plastically, and stage 4 is fiber fractures followed by composite failure. So the reason why we are looking at this plot and trying to distinguish is because when we are applying our mechanics to predict the strength, we need to know whether the material is behaving elastic or plastic. That's where, when we know that, we can change our approach to predict failure. Since it's an introductory course, we'll only focus on the stage 1 where both the fiber and the matrix are linear, and try to use this approach to predict failure. So let's make few observations. What happens with brittle fibers? So we already mentioned brittle fibers, they only have this elastic region and they don't have the plastic region. So the stage 3 does not exist, because in stage 3 the fiber should show plastic behavior, which is only possible with ductile fibers but not with brittle fibers. Now with brittle matrix, so brittle matrix meaning this matrix material fails at this point. So meaning we don't have these stages 2 and 3 where we say that the matrix is plastically deformed. So both these stages 2 and 3 does not exist for a brittle matrix. So as we are saying, this is a more generalized way of looking at failure in the composite, depending on whether the fiber is brittle or ductile versus the matrix is brittle or ductile. We can look into special cases from this generalized plot. Now that we have started discussing about the failure in a composite, we will look into a model to predict the failure. In this model, what we do is we assume that all fibers fail instantaneously, meaning that we are saying all fibers have equal strength. Though, so now the question is this a realistic assumption or not? The answer is no. Usually, it's not possible that all fibers will fail instantaneously, but we are making these assumptions to make the analysis simplified. Later we will come back and see what if this assumption is not true and what other approaches we have to follow. But for now, let's assume that the all fibers fail at the same strength, and we'll limit our analysis to brittle materials. Let's say both the matrix and the fiber are brittle, and we also limit our analysis to linear elastic materials, meaning both the fiber and the matrix will only considering the linear elastic behavior. So let's plot the stress strain relation for the fiber and the matrix. So we'll start with the matrix material. Let's start with the matrix material. It's a straight line since we are assuming it to be linear elastic. So this is the point of failure which has a corresponding strain. We'll write it as epsilon matrix material comma max, meaning it is the maximum strain the matrix can take before failure, and the corresponding stress we'll write it as sigma m max. So this is the stress at which this matrix material will fail. Now let's do the same for fiber. So here too we'll note the strain at which it fails. We'll write it as epsilon f max, and the corresponding stress we will write it as sigma f max. Okay. So of course this is the fiber and this is our matrix. Okay. Now that we have seen the stress strain response for the matrix and the fiber, now the question is, for the composite, how will the response look like? Since both the matrix and fiber are linear elastic, so even for the composite we will get a linear elastic relation. But when will that composite fail? If I ask, how can we respond? So will it, and now let's say we are following this maximum strain as the failure criteria. So the composite will fail when it reaches the first failure strain, which is the fiber strain. So let's say we are talking about some intermediate volume fractions, then the composite response should be something like this. Okay. So here I want to make one important point. We should think about this composite because it has a volume fraction Vf, what is the range of VF? It can go from 0 to 1. So now the question is, if VF equal to 0, what does it mean? It means that we are talking about a complete matrix material. For the complete matrix material, the response will be here. So meaning this will be the response of the composite, where we say the VF value is 0. And similarly, what happens when VF equal to 1, meaning the complete composite is made up of the fiber, then the response is again here. So it will overlap with the red line, meaning that the corresponding stresses at which this composite fails varies from this corresponding value to the stress at which the fiber fails. Now let's see what is the expression we can give for the composite. So we said the composite fails, epsilon C max is the maximum strain the composite can take. We already showed that the composite fails when failure strain in the fiber. So for this, how can we write the relations? We can write the corresponding stress in the composite as a simple rule of mixture kind of equation, where we write in terms of stresses in the fiber times the volume fraction in the fiber, and stresses in the matrix times volume fraction of the matrix. See, 1 minus VF, we already know it's simply the volume fraction of the matrix material. So if we look at this point, we notice that these are the stresses in the matrix corresponding to the strain epsilon F max. Yeah. So the same stress is shown here. So in summary, what we have seen till now is we are able to give an equation for this composite. So the stresses in the composite we are able to give in terms of the failure stresses in the fiber and the stresses in the matrix at which it fails. But now there is some important observation to be made. What is the reason why we use fibers? The reason why we use fibers is so that we can improve the strength of the matrix material. But if you notice, let's talk about volume fraction. If you look at a volume fraction, let's say a curve like this. Let's say this corresponds to one volume fraction Vf. So here what we see is the composite fails at a stress which is less than the maximum stress the matrix can take. What is the maximum stress the matrix can take? Sigma m max. But here we see the composite is failing with a stress less than the failure stresses of the matrix. Then it beats the purpose of adding fibers. So when do we get benefit of the fibers? When the failure stress is at least more than the stresses the matrix can take. How do we ensure that? So here we are saying the failure stress in the composite should be more than the failure strength of the matrix. How do we ensure this? To do this, we simply replace this in this equation, just replace it with sigma m max. And the corresponding Vf value is given by this expression. So essentially, what is Vf critical? Vf critical, let me erase this and draw it so that we don't get confused. So now let's draw the composite response at this critical value. So it will look something like this. So this particular composite will have a corresponding value of Vf, which we are now saying it as Vf critical. So which means if your volume fraction is more than this critical value, then the composite will have a strength greater than the strength of the matrix. But if your volume fraction is less than Vf critical, if the volume fraction is less than composite strength, is less than matrix strength. But if your volume fraction you have chosen is greater than Vf critical, then we are saying the composite strength is at least more than the matrix strength. Of. There is a other better way to represent this, which we will show it in the next slide. So here we have reproduced those main expressions. This is the equation we derived to show what is the failure stress in the composite for a given value of Vf. And this is the expression we got for this Vf critical, beyond which the composite is stronger than the matrix material. So one way of looking at it is, let's say the x-axis we plot for the volume fraction, Vf equal to 0 and Vf equal to 1. And for the y-axis we'll consider the failure stresses in the composite. So that's the maximum stress the composite can take. So from this first equation we know that when Vf equal to 0, this value should be this. What is this? This is the stress in the matrix corresponding to the failure strain of fiber. And when Vf equal to 1, we get these failure stresses in the fiber. And this is a straight line because the equation we have is a linear expression with Vf. So this we said is the sigma f max. Okay. So let's say this is equation 1 and this is how we represent this equation 1 with this straight line. Now let's go back to the previous slide where we discussed about this Vf critical. We are comparing with the failure stress of the matrix. So in this plot, where is the failure stress of the matrix? It is somewhere here. Because we have seen the matrix actually fails with a slightly more stress. Okay. And the corresponding volume fraction is actually the number we are discussing, Vf critical. Okay. I hope this is clear, right? Here we are showing this equation in terms of this straight line, where it is interpolating between the fiber failure strength and the stresses in the matrix corresponding to failure strain of fiber. Okay. And then we are also shown this Vf critical, which we are focusing on. What happens when there is a very small volume fraction? Let's say we built a composite and let's say there are only 1 or 2 fibers, which means almost 0 or negligible. The moment you load, these fibers will fail because the matrix is more ductile, it takes more strain. How does it accommodate strain? By the fiber failing. So when the fibers fail, and since these are too less, these are almost like there are no fibers, so it's almost like a void. So if we consider now the composite response as though there are voids instead of the fibers, then the relation to write this composite strength is slightly different. There we can write it in this fashion, where we can start with failure strength of the matrix on the left hand, and at the right hand, since it is a void, it should go to 0. Now let me change the color. Okay. So here what are we assuming? That the fibers do not play a role. So this is true when we are working with very low volume fractions. But we notice that these two lines intersect at a point, which we'll call it as F minimum. So what does this blue line mean? Blue line means it is matrix dominant. And the black line shows that it is fiber dominant. So if we now look at what happens if you go from the volume fraction of 0 to 1, initially it is matrix dominated. So beyond this value of Vf minimum, then it becomes fiber dominant. Okay. So the point we are trying to make here is we are now trying to introduce this concept of Vf minimum. What does Vf minimum does? It says whether the composite is matrix dominated or fiber dominant. So here we are saying after fiber failure, composite will fail. So here this is the equation for this blue line, where we said the other end is we are considering the fibers as voids because the fibers have already failed and they don't take the load. Okay. From this expression we were able to write the expression for Vf minimum. Though I have shown you pictorially, here are the equations to find the actual value of Vf minimum. But let's focus on the what is the meaning of this Vf minimum. So if your volume fraction is less than Vf minimum, then the composite is matrix dominated. Whereas when your volume fraction is greater than this Vf minimum, then it is fiber dominant. So you may be thinking, why are we interested in these critical values like Vf critical and Vf minimum? So the answer is, when we are adding fibers, the reason why we add fibers is to improve the strength of the composite. And we are adding these fibers to the matrix, meaning that our hope is it should do better. The fiber should first play an important role, and the strength of the composite should be more than the properties of the matrix. So the Vf minimum takes care that the fibers are really playing a role in the strength prediction or the strength of the composite, and Vf critical ensures that the failure strength is at least more than the failure strength of the matrix. So again I have to repeat that we have done this analysis assuming that fibers are of equal strength, but in reality we know no two materials are the same. No matter how precisely we are no matter how precisely we control the manufacturing process, there is always a statistical distribution, especially with failure. So now let's see how that affects the failure and what are the concepts we need to be aware of. Mind you, here I am not trying to introduce to any failure models, but only a few concepts what one should be aware of while we work with composites. So we'll start with fiber length. So meaning like if there are 10 different fibers, all with different lengths, we know that the strengths do depend on the length. So and how do the dependence be? So as we increase the length of the fiber, the strength goes down. Let's say these are the experiments we have done at 5 different lengths, and we notice that the strength value, or this is the fiber strength. And why does the fiber strength decrease with fiber length? The reason is because more is the strength, the greater is the chance for flaws in the material. As we know, the any material fails at the weakest link. Where is the weakest link for a material? It is the flaw. And as we increase the length of the fiber, there are more chances to find these flaws. So that's one reason why as we increase the length, the strength decreases. This is only one of the reason to reason out and show that why there is a strength distribution, but of course there are other reasons as well. Now let's say we are considering a lamina with multiple fibers. Let me show few fibers. Let's say these are continuous fibers. And let's say the loading is in the x direction. Okay. But now let's consider that one of the fibers failed, meaning that a fiber here failed at somewhere here. So we are looking at two fibers which are intact, but the fiber in the middle, we are saying that there is a failure at the mid-length. The idea here is to see how the stresses vary in the fibers and the matrix. So first let's look at how the stresses vary in the fiber. Since we are applying a load in the x direction, wherever there is a failure, there the stresses are zero. So let's say we are trying to show for the fiber. And what are the stresses the fiber is taking? It is simply taking the normal stress sigma, which let's say this is the x-axis. So what happens is it goes from zero stress, which gradually builds up, and then after a while it comes to this constant value, which is the applied stress sigma x. So these are the stresses in the fiber. But now the question is, how does the matrix respond to failure? So let's say here I will try to show how does the matrix, what are the nature of the stresses the matrix takes? Will it take the normal stress or the shear stress is the question. So in fact here we'll notice that the matrix takes shear stress, because when there is a failure, because of this shear stress in the matrix, the load is transformed from one broken end of the fiber to the other broken. So let's say this is the x-axis, and we are now plotting the shear stress in the broken in the matrix material. Let's say we are talking about something like this. Then the shear stress is high at the broken point, and as we go along, it again comes back to zero. So meaning that this is the zone where there are shear stresses present, but as we go along or as we go away from this broken area, there are negligible shear stresses in the matrix. The point I am trying to show here is to give you an idea about when there is a failure in fiber failure in the composite, how the fiber takes the load as well as how the matrix responds to this failure. Okay. So these are actually, you can see these are some individual concepts. We just need to be aware of how failure happens, and once there is a failure, how it affects the stress distribution. Based on this, there are in fact some failure criteria which are developed based on these stress distributions. But since this is an introductory course, we are not trying to go into the deeper details. That one can refer to any of the standard textbooks or research papers. And lastly, which is a very important concept about cumulative number of fiber fractures. So which means when we, let's say this is a composite and I'm loading it, so there is an ultimate load, meaning the load at which it breaks into two pieces. Does it mean that all fibers fail at that ultimate load? The answer is no. But now the question is, when does the first fiber fail, or at what instance or what ratio of the ultimate load does these fibers accumulate? So we are talking about ultimate load. So let's say we start from zero load and now we are looking at normalized ultimate load, meaning the one represents the ultimate load. So from experiments, we see that the first failure happens approximately at 0.5. What does 0.5 mean? This is the half of the ultimate load, and then it suddenly rises. Okay. So I need to stress on this word cumulative, meaning the number of fibers, and we are counting the number of fibers. We said the first fiber fails close to zero point 0.5. We are not saying exactly 0.5, but somewhere close between, let's say, 40% or 60% of the ultimate load. But then as we continue to load, it's not like because one or two fibers fail, the composite completely fails. What is happening is, though there is one failure, the other fibers are taking up the load and we are able to actually increase the load. So the load is not decreasing, instead it is increasing, meaning that the composite can take even higher loads. And as you can see, towards the end, the increase is exponential. This is important to know for maintenance of composites, because let's say, uh, and actually this is good that it is happening, because there is some indication of failure before there is a sudden failure, meaning like, let's say these composite structures, for example, like aerospace structures made up of composites, there are frequent maintenance which is done. The idea is to see if there is any indication of failure in these composites. And now that we know this cumulative things has a progression, so which means that if the maintenance are timed well, it is possible for us to identify the failures even before the ultimate failure or the disaster. With this, we conclude our discussion about failure of lamina. Here we have noticed that there is a strength distribution and how it affects the failure of the composite. So now let's summarize the micromechanics of lamina. We started with the stiffness prediction using both the mechanics of materials approach and using Halpin-Tsai equations. We also have seen a semi-empirical approach. Coming to the strength prediction, we identified that the fibers, there is a strength distribution in the failure of fibers, but we also looked at if all the fibers fail instantaneously, meaning they all have the same strength, then how can we predict the strength of the composite? Later, though we didn't discuss any models for this strength distribution, but we did look at different aspects of laminar failure, where we have seen that there is a strength distribution. Like we said, as we increase the length of the fibers, the failure strength decreases. And we also looked at how the stress state in the fiber and matrix vary where there is a fiber failure. And lastly, and very importantly, we have seen how the accumulation or the cumulative fibers fail in a composite. We said if you are comparing with an ultimate strength of a composite, the first fiber failure happens somewhere at half the ultimate strength. But gradually these number of fibers failures increase, and towards the end it is exponential and it fails drastically. So this should conclude our discussion on the micromechanics of lamina. In the next video onwards, we move into a new topic where we discuss the mechanics of the laminate. Thank you.